So how do we go about defining the abstract syntax for a graphical language, and why? The most obvious difference between graphical languages and textual languages is that, well, graphical languages are graphical. They involve shapes and things laid out on 2D planes. That, it turns out, is not actually the most relevant part, the most relevant difference between a graphical language like UML or something similar and your favourite textual programming language. The key difference is actually that graphical languages don't have a natural tree-like structure. What do we mean by this? Well, if you've done a compiler course or you've ever thought about compilation at all, you've probably built a syntax tree for an expression in a textual programming language. And even though you can start arguing about, well, you know, we have references to symbols and symbol tables and what have you in our language, fundamentally it makes sense to say this is the tree representation of my textual programming language construct. You know, there's typically, you know, there's a right way to parse it, which splits it into chunks and then splits those chunks into chunks and so on. A thing like a UML diagram, or a diagram in general laid out on a 2D plane, is not like that. There isn't an obvious place where you start, or an obvious way to split it up. There might be many different ways to split it up. And that makes it quite difficult to approach those languages in the same kind of way as you would typically approach a textual expression. And really this is why we've ended up with meta-modeling as the solution to how we define the abstract syntax of graphical languages. And you've already seen this a bit, of course, as we met the meta-model for UML and as we did the paleo example at the start. But let's talk a bit about meta, especially the meta in meta-model. So it's tempting to say, and we often do say, a meta-model is a model of the model. But what we really mean is something more like a meta-model is a model that describes all the possible models at some other level, so of the system. So let's just think about class diagrams for a moment. So if you have a model, a class model of a system, then what's that doing for you? It's describing something about how the objects in the system can be configured. So, you know, what classes they can be instances of, how many there can be, how they're connected. So then a running instance of the system conforms to the model. Or we might say it is an instance of the model. Okay? So then the system described by the model means all the configurations that the objects can be in according to the model. So the model constrains those configurations. Only some possible configurations are actually legal. Okay? So you rule out configurations in which you've got objects that are of classes that don't appear in the class diagram, and collections of objects that don't obey the multiplicities on the associations, and all that kind of thing. Okay? So a meta-model of a modelling language is the same thing at the next level up. So this is what we get when what we're trying to do is we're trying to say which models are legal. So then we say a model conforms to a meta-model if it has the right things in it. So the graphical elements that occur in it are all instances of things that have been specified to be part of the language by the meta-model, and they are related in the appropriate way. And it's really just the same thing, it's just the same relationship. And you may need to think about this a bit to convince yourself that it's really so. But I think we talked about this a bit at the paleo case. So a meta-model defines the abstract syntax of a language. And because it's exactly the same as the relationship between a model and the running instances, the real-world objects that conform to that model, we can actually make use of that, and OMG does, and actually have yourself a 4-level meta-model hierarchy that exploits that similarity. And so this is the classic OMG 4-level meta-model hierarchy. At the bottom we have our real-world objects, or people sometimes say the instances in the running system. And this is a picture of a video. A video, children, was how people used to get hold of their films in the days before you could just download them or stream them. It typically would involve a recording of the movie on some plastic tape. Anyway, one of those is a video. And the class video at the model level describes all possible running instances of things that we want to refer to as videos. So it says they're all going to have a title which is some kind of a string, but the model doesn't specify a particular title. It just says there will be a title and it will be a string. Okay. Now similarly, a UML model, this is a very simple UML model with just one class containing just one attribute, is a correct instance of the UML metamodel. Okay, and that is to say, it contains a class, so the class is an instance of the meta class in the UML metamodel, and the attribute here, whose name is title and whose type is string, is an instance of the meta class attribute. Okay, and we're eliding a lot of detail, of course. You know, there's got to be some kind of relationship between attribute and class in the metamodel, and you've already seen the UML metamodel, so you know the kind of thing that we have. But at the next level up, we can say, well, suppose we now consider the class of all the collection of all metamodels that we might like to be able to define. So if we're going to say, well, now we're interested in the task of defining languages, what does it mean to define a language? Well, we want to be able to specify a metamodel. How do we specify a metamodel? Well, a metamodel is going to be a thing that conforms to the meta-metamodel. Okay? So up here at the M3 level, we're going to say, well, there had better be some classes, and there'll be a notion of instance, and there'll be a notion of whatever, you know, there's association and probably also typing, what have you, at that level. And we talked a bit about morph earlier, and I mostly said I didn't really want you to know too much more about morph than that it's like a cut-down subset of the UML class notation, and that will kind of do. Okay, and the instance of relationship goes all the way up. Don't worry too much about this circular instance of thing at the meta-metamodel level. This is really just saying the meta-metamodeling language, morph in our case, is going to be simple enough that you can model it in itself. And really all you're saying is, you know, it's got to bottom out somewhere. You've got to get to some point where you say, okay, now we know what this means. Okay. So here's a slightly different picture of it, again with our M0 up to M3, and the distinction that's being drawn here in this picture is between domain engineering, so this is your kind of standard software engineering where you define models and build systems that conform to them, and language engineering where we're going to be defining domain-specific languages typically in a very similar way. So I think I said most of this previously. So you have some kind of snapshot. This is about the running system. You have the system that you're typically defining. So uni system, a system of to describe universities is the example in the book that this picture comes from. It's another very nice book. Languages in which models can be defined include you know, UML and entity relationship diagrams and your favorite domain-specific language, and so it goes on. And languages in which to define languages, the key one in the OMG stack is morph, and then ecore is the corresponding thing in the Eclipse world, which is very closely related to morph, but not absolutely identical. Okay. So, just to say a little bit about the connection to the Eclipse world, the OMG hierarchy aims to be language neutral. It aims not to favour Eclipse over other language development technologies, but of course there are things that have to be done that are not OMG's concern in order to support language engineering, for example, to allow people to develop IDEs for supporting their new domain-specific language and do code generation and all this kind of stuff. And the Eclipse modelling framework supports that kind of task. Within the Eclipse modelling framework, ecore is the metamodel, and so ecore is the metamodeling language which is used for defining models that are held in Eclipse. And these might be things you'd like to think about as models, and they might be things you'd like to think about as metamodels for defining languages, but I hope I've convinced you that actually that can often be more of a question of perspective. There's not a technical difference between a model and a metamodel. It's about how you're thinking about them at the time. If you're thinking about a model as being a means of defining a language, then it's a metamodel. Okay, and roughly speaking, eCore corresponds to part of MOF in OMG terms, and you could look this up if you want to know details, but I don't expect you to for this course. So how do you go about defining a domain-specific modelling language? Well, one thing you can do is to define your metamodel using eCore in the Eclipse world. And then you can use something like, there are EMF, GMF tools, or there's Eugenia out of the Epsilon family, to define the diagrammatic elements and how they correspond to the abstract syntax. And then you can define semantics, for example, by generating Java code from your model, probably partial Java code for people to fill in the details of later. And in order to allow people to use your DSML, you'll want a suitable model editor, and the EMF tools and lots of related tools to make things easier will allow you to do that within the Eclipse world. And there are other ways of doing this as well, and there will be a lab on at least one way of doing this. Hopefully, at the time of recording it, I haven't completely decided what labs there are. If you want to define a textual domain-specific language, it's not that different. You're going to need to define a grammar to give your concrete syntax. Now, when you're working with textual languages, you often don't really think about abstract syntax as a thing that you have to define separately, because it will often be generated from the grammar. And that's fine. You've come across, I'm sure, the idea of abstract syntax trees. Well, you know, the way the abstract syntax tree is defined is the abstract syntax. But if you've defined your concrete syntax first, you might not need to think about that as being a separate task that you have to undertake. But the abstract syntax can indeed be expressed in eCore, and you can go back and forth between these things. And then you can define semantics by generating Java code and so on. And again, to allow people to use your language, you need to be able to generate an editor. And it has to have, appropriate validation and what have you. And there is an amazing collection of tools that will allow you to do quite sophisticated things quite easily once you understand how to use the tools. But the tools themselves are not always that easy to learn. We've talked a couple of times about code generation. Well, how do you write a code generator? You can do it, of course, in your favourite programming language, because all we mean when we talk about a code generator is a program that takes in the thing from which you would like to generate the code, whether that's textual or graphical, and spits out some code, which is itself text. Okay, so you can do that how you like. But one way of doing it in the Java world is to use xtend, and here's a quote from somebody who was involved in developing it about what xtend is. It's essentially Java on steroids with awesome expressive notation that lets you express your logic in super elegant ways, not possible in Java itself. So it's got a bunch of handy features like the convenient ways to have multi-line strings, which is, as you can imagine, an extremely useful thing to have when you're trying to do code generation. If you want to have a whole bunch of boilerplate stuff that should get spat out, you don't want to have to construct it with your string builders manually. And nice use of extension methods and what have you. So we may or may not see some of that in the labs, but it's worth knowing a little bit about. So why are we sort of spinning between DSLs and DSMLs and discussing them in the same lecture? Isn't this kind of unnecessarily confusing? Well, the key thing is that actually whether a language is expressed graphically or textually doesn't these days seem to be as important as we used to think it was. And in a way, it's the very separation of concrete and abstract syntax that allows us to see the differences as being less important than we might think. Because once you've got explicitly a notion of abstract syntax for your language that says these are the concepts and these are how they're related, then you can have multiple concrete syntaxes for the same abstract syntax. Now, whether you count different concrete syntaxes for the same abstract syntax as being the same language or not, is very much a matter of taste. But to my mind, mostly yes. So if you work with eCore, you'll find that in the Eclipse world there are many different editors for eCore models. You can edit your eCore model by having it presented to you graphically, and by using a graphical editor to alter it, to add and delete things and change how they're related. Or there are several different textual syntaxes for eCore, so textual representations of the same underlying abstract syntax, which you can then edit in a textual editor. And the difference is just concrete syntax, right? And so the difference between what it is to be concrete syntax for a language and what it is just to be a different editor for the language also gets blurred. And you can end up thinking, well, actually the thing that's important, the thing that defines what it is to be the language, is actually the abstract syntax. And so you can, and quite often it's convenient to do so, you can have a graphical and a textual syntax, concrete syntax, for your language. And you might, if you were defining a domain-specific language for use in an organisation, want to define both. You know, perhaps you've got different classes of users. Perhaps you've got non-programmer users who are more comfortable if you provide them with a handy graphical editor for the graphical version of your syntax that looks more like a picture that perhaps they're happier with. And maybe you've got programmers who would rather be able to type and use auto-completion and what have you, which looks to them more familiar from their programming language experience. And using modern tools, that's not actually too difficult to do. And so, what's really the difference between a programming language and a modelling language anyway? What is a programming language? Maybe it's a model. Well, kind of everything's a model. And one can get very airy-fairy, and I've indicated, I think, that that there are some very, very clever tools for helping us define languages these days, and I hope you'll see some of them in the labs. I'm constantly reminded of Arthur C. Clarke's third law, which is this, that any sufficiently advanced technology is indistinguishable from magic. And also, the second law, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. That, unfortunately, is quite easy to do with today's domain-specific language engineering technology, because the thing that distinguishes it from magic is, in fact, the flakiness of the tools, as I'm afraid you'll probably see in the labs. Will that ever go away? Well, it is to be hoped. At the moment, it feels a bit like that to me it feels a bit as though the world of tools for this is sort of perpetually flaky. There are things that can do amazing things in the hands of tool experts, but we aren't really there with making this technology available to any developer who wants to use it without a very steep learning curve. I hope that will change, and in fact I'm involved in an undertaking called MDE-Net, the Model Driven Engineering Network, which is aiming to contribute to helping that to go away, but we'll see. Yes, and you should look up Clarke's first law. This has been a bit of a whistle-stop tour of the idea of domain-specific languages. We could very easily have an entire course on it. In an ideal world we would, and there are specific whole courses on domain-specific languages. Some of them are even available on YouTube these days. You might like to have a look. There are a whole bunch of good books these days as well, and some of them are freely available. So there are a few, and you might like to look some of those up and have a read if this interests you and you think you might like to get ahead of the game and know about this stuff for when it turns up in the mainstream in your future software development career.